One of the most basic concepts that we have in statistics is the idea of a measure of central tendency. The most basic, the most common type of central tendency is the mean, the average value. And while that formula looks a little bit daunting, it's got a capital sigma in it, it's got X, N's. What it's really telling you at the end of the day is if you have a bunch of data items and you need to take their mean, their average, you need to add them all up and divide by however many you have. It's that simple. So that is what the mean essentially is, and not really any more complicated than that. The good news is that we have calculators. We can work these things with the calculators, and they're pretty straightforward. So that's pretty much what you want to do. Add up everything you have, divide by however many you have. Excuse me. No, I don't. I'm not sick or anything. It's just this stuff near me smells weird. So calculating the mean, we could talk about some data that was taken for some countries like China, Singapore, Russia, South Africa, the UK, etc. And a question was asked, are inventors born or are they made? And it's kind of an interesting question to see how different countries respond. It looks like people in China think that inventiveness can be learned, that you can learn to become an inventor. 92% of them feel that way. In the US, only 75% of people feel that way. So kind of an interesting idea. We can actually take the mean of these numbers, 92%, 84%, 84%, 80%, and so on. We can take the average, we just add up all of them, the 92 plus the 84 plus the 84, and so on. There were 10 total data points. So the average percent at which countries answer this question, the percent of their population that say, yes, you can learn to be an inventor, is 79.9%. Now, if you're dealing with a frequency distribution, calculating the mean works a little bit differently. Here, let's say you've got students are asked, have you felt stress? Or how stressed have you felt in the last 2.5 weeks? Well, with finals coming up, I imagine you're going to see more people on the higher end. That a 10 is just you're absolutely stressed out. A 0 is that you're not stressed out even in the slightest. And so 2 students answered 0. 1 student said they are feeling a 1 out of 10 in terms of stress. 3 students said a 2 out of 10. 12 students said a 3 out of 10. And so in total, 2 plus 1 plus 3 plus 12 plus 16 plus 18 plus 13 plus 31 plus 26 plus 15 plus 14, whatever that's going to come out to, that is going to be the total number of students who responded to this survey. So what we're going to say is if we wanted to calculate the average stress rating among students that have answered to this survey, well, we don't just say 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, blah, 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 and then divide by however many there are. No, what we need to do is we need to take their weights into account. We need to say, well, not that many people said 0, so 0 shouldn't have a huge impact on this. Very few people said that their stress rating was 1. Very few people said their stress rating was 2. On the other hand, a good number of people, the most number of people, said that their stress rating was a 7, that their stress was at a 7. So the 7 should be something that has a higher impact on the average. So that's why when calculating the the average for a frequency distribution, you take the actual rating itself here, you multiply by the number of people who responded that, the frequency itself. So you do 0 times 2, then you do 1 times 1, then you do 2 times 3, and so on and so forth for all of this information. The reason being that's going to help us to weight. That's going to help us to give weight to each of the answers. So you do this all the way down. The formula is to add up all these multiplied out frequencies and divide by the total number of people who responded to the survey, which is the sum of this column here. So if I were to add up this frequency column here in the middle, that's the total number of students, it was 151. If I add up all these weighted kind of frequency values, that comes out to 975. So now I do 975 divided by the 151 students. And so on average, students indicated that their stress rating was somewhere between 6 and 7, a 6.46. So the average was somewhere between 6 and 7, which probably isn't very good. A 6 to 7, that's still fairly stressed out. I think that's what most people feel. Of course, during the holiday season, people report much higher levels of stress because, you got to spend money to buy gifts. And everyone says, you don't need to spend money to buy gifts. And they're like, yeah, but it's easier. I can't make handmade things because I don't have any talent for it. So you just get them all gift cards. But it's stressful to spend that money, for sure. So we have the mean, which is an average, and it weights. If you have a frequency distribution, it weights the more popular choices and gives them more of an influence on the mean. The less popular choices have less of an influence on the average. Now, completely opposite of that is not opposite, but a completely different measure of central tendency. A completely different measure of central tendency is the median. The average is not necessarily the middle of a data set. The median, though, is exactly the middle. The median, if we take our data, which it has to be numerical data, and we order it from smallest to largest, the median is going to be the exact middle value. Now, the problem is if you have an even number of data points, there's going to be two values that are exactly in the middle. So what you need to do is you need to take the average of just the middle two items, and that's your median for an even data set. If you have an odd data set, an odd number of things in your set, then there is going to be a perfect middle value there, and that's going to be what the median is. So the median is, again, one of our basic measures. So let's say you have this group of 5 values, 84, 90, 98, 95, and 88. The first thing you need to do is put them in order from least to greatest. Put them in order from least to greatest. And then you have 5 data values, you'll notice. You have 1, 2, 3, 4, 5 data values. 5 is an odd number, so there will be a number that is perfectly in the middle. And that is going to be our median. If I had 113 data values, that's an odd number, so there is going to be a value that's perfectly in the middle. Now, you're not going to be asked on the final exam to find the median of 113 data values because that's a ton. It's a huge undertaking. You might be asked to find the median of 9 or 11 or 13 values, which is still very doable. Now, notice here, if we find the median of this data set, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got now 10 data values. 10 is an even number. Remember, an even number is a number that is divisible by 2. We have 10 data values. So first, you need to put the data in order from least to greatest. So 7, 13. If you were to have any repeated values, which we don't here, but if you were to have repeated values, multiple values that are the same thing, you still write all of them out. You don't just put one representative for the group. You write all of them out. After you've put them in order from least to greatest, there's going to be 2 values that are perfectly in the middle. And that's just by the nature of it. That's going to happen for every even data set. And so there's not much you can do about that. What you're going to have to do is take the average of those middle two values. So you don't average all 10 values, you just average the two that are in the very middle, add them up, divide by 2, and you're going to get 31 is your median. So the median is pretty straightforward. It's actually kind of a fun calculation to do, just depending on, you know, if you enjoy putting numbers in order and adding things up. There is a silly kind of formula here. You can always say that if you have an odd data set, the median is going to be in the n plus first divided by 2 position, which is kind of silly. If you have an odd data set, first you still got to put them in order from smallest to greatest. Here we have 9 data values. So the median is going to be in the 9 plus 1, which is 10 divided by 2. It's going to be in the 5th position. 1, 2, 3, 4, 5. That's not a formula you have to memorize by any means. It's just a different way of looking at the same thing. If you're taking a more advanced statistics course, it is useful to know formulas like that for something called order statistics. So the median is pretty straightforward. Now, you might need to use that little formula for finding the median of a lot of data values. So you'll notice here we had 151 total data values in this frequency chart. If you add up all these frequencies, it comes out to 151. So you might need this little n plus 1 over 2 formula. 151 plus 1 is 152. Divided by 2, it's going to be in the 76th position. Since this is already in order from least to greatest, the first 2 positions would be zeros. The third position would be a 1. The next 3 positions would be a 2. The next 12 positions would be a 3. The next 16 positions would be a 4. So 2 plus 1 is 3, plus 3 again is 6. So we're 6 positions in at this point. Plus 12, we're 18 positions in now. Plus 16, 18 plus 16 is what, 34? So we're 34 positions in now. Add another 18 to that, we're at 52 positions in. Add another 13 to that, we're now at 65 positions in. And now add a 31 to that, and we're now at 96 positions in. We need the 76th position, so the 76th position must be somewhere in here. Thus, the median is going to be the actual 7 itself. If you want to think about this frequency distribution written out from smallest to largest, these are the actual data values. This frequency column is just telling you how many of that data value exist. So if you wanted to write out the data fully, you'd have 0, 0, you'd have 2, 0, then 1, then 2, 2, 2, you'd have 3 2s, then you'd have 12 3s, then you'd have 16 4s, 18 5s, 13 6s, 31 7s, and so on. So you can find the 76th position, it's kind of just like a little bit of a logic puzzle. There's no magical, mathematical, cool, slick little way that we can do this. And so you can see they basically did what we just did here. The median stress level rating is a 7. So what's interesting about the mean and the median? They're both measures of central tendency. There are 2 of our basic measures. The third one is the mode, which we'll talk about, but the mode is less interesting for a small amount of discrete data. But anyways, we can compute the measure of central tendency, we can compute the mean, and we can compute the median for a data set. But at the end of the day, what will happen is if there are values that are called outliers, that are either really, really large compared to the rest of the data or really, really small compared to the rest of the data. If there are outliers, those outliers are going to have a much larger effect on the mean, on the average, than they are going to have on the median, the middle value. And so it just depends on which one is better, the mean or the median. It depends on your data set. If your data set has some outliers in it, the median is the better choice because the median is not going to be affected by those outliers as much. If your data set doesn't really have any outliers in it, you want to use the mean. You want to use the average value. So let's look at this. 5 employees in a manufacturing plant earn salaries of $19,700, $20,400, $21,500, $22,600, and $23,000. Now the manager, the section manager of this plant, this manufacturing plant, earns $95,000, which is almost as much as the rest of the employees combined. So that's kind of an interesting thought. This one salary, this $95,000 salary, is way the heck up there. And you notice it when you put the numbers in order from smallest to greatest. You'll see that 19,700, 20,400, blah, blah, blah. Those first 5 salaries are all within reasonable. You can just see they're all pretty reasonably close to each other. But then you have $95,000, which is pretty whopping. It's huge compared to the rest. So there's definitely an outlier in this set. Now, there are more formal ways of locating outliers, and you would learn about those if you took a standard statistics course. But for our purposes, we're just going to say that clearly is an outlier, but not go really beyond that. Now, we want to find the median annual salary first. So we put them in order from smallest to greatest. There's 6 data values, so the median is going to be the average of these 2 in the middle. Do you have to do this in your head? Do you have to do any of these calculations in your head? Not at all. You have a calculator. So we are just going to take those middle 2 values, 21,500, which they did the calculation correctly, just wrote this number incorrectly. 21,500 plus 22,600, which comes out to 44,100. Divide it by 2, and you get $22,050. That's the median salary. The $22,050 looks like most of the rest of the data values, except for the 95,000. It's very close to all the rest of the data values. So the median is one thing. The mean, on the other hand, this $95,000, its actual face value gets calculated in. For the median, the face value of each individual number only gets calculated in if you happen to have 2 perfectly in the middle. If you don't, their face values don't really, there's no mathematical formula that's incorporating their face values. But for the mean, there is. So this $95,000 is going to bring the numerator here up by a lot. And so when you add them all up, divide by 6, this 33,700, that's a good deal more than any of these first 5 salaries are, and a good deal less than the outlier salary. So this does not appear to be a very good representation of the data set it came from, which is secretly what we're trying to create with a measure of central tendency. We want a good representative for the data set. Next up, the mode. The mode is actually a little bit trickier than the initial definition suggests. The mode is the data value that occurs most often in a data set. So you've probably heard of the big 3 M's, the mean, the median, and the mode. Now here's the problem. It has to be a data value that occurs more frequently than others. But you can actually have multiple data values that are occurring more frequently than other data values. And so you can actually have a case where you have more than one mode. If no data value occurs more often than any other, if every data value occurs the same number of times, there actually is no mode to the data set. It's also a bit tricky for discrete data to see why the mode is a measure of central tendency when you could happen to have a data set that has two really large values that are the same, that are not anywhere near the middle value of the data set. And that can end up being your mode just because it happened to show up a couple times. Now, if you were to take a very large data set from a certain distribution, that should smooth out. But for small amounts of discrete data, the mode is just not that interesting. So for this one, find the mode for the following groups of data. You have 7, 2, 4, 7, 8, 10. The 7 shows up twice. The rest of the data values show up once. So the mode is just 7. Like mode 7 graphics. So that one's not interesting. Let's make some that are interesting. So I added some more to this, 7, 2, 4, 7, 8, 10, 7, 9. Well, once again, the 7 is the only thing that's showing up more than once. In fact, it shows up 3 times. Everything else shows up exactly once. So the mode is still 7 there. So not a whole lot more interesting. Let's play around though. Here's a data set, 7, 2, 4, 7, 8, 10, 7, 8, 11, and 5. Well, we've got 3 7s showing up. We've got 2 8s showing up. Everything else shows up just once. The mode or modes has to be whichever value or values shows up strictly the most. So even though the 8 shows up more than once, it's still not a mode because the 7 shows up strictly the most. But now if I play with this data set a little bit, I change this 5 to an 8. Now I've got 3 7s. I also have 3 8s. Everything else shows up once. So the solution, the modes, is both 7 and 8. They're both the modes. One of them is no more the mode than the other. So there you go. Different possibilities. Let's play with it even some more. And then let's delete this 7. So now my data set is 7, 2, 4, 8, 10, 12, 9, 1. Do you see any data values showing up more often than other data values? Is that happening here? Sure doesn't seem to be. So there's actually no mode here because nothing is showing up more often than others. So kind of interesting ideas. There's even one more interesting idea that I could play with. You can get really creative really quickly, even when it's kind of stupid. You have 2 7s, 2 2s. So this is one single data set. I've just put it over 2 lines now, so it's easier to read. 2 4s, 2 8s, 2 10s, 2 12s, 2 9s, but only 1 1. So there's a bunch of things tied for the most, and then the 1 is only shows up one time itself. So the modes, there's 7, 2, 4, 8, 10, 12, and 9. These are all modes here because each of them shows up more frequently than at least one other data value from the set. So a pretty neat idea here about how the modes can work. Finally, if I do go ahead and just replicate it, 2 7s, 2 2s, 2 4s, 2 8s, 2 10s, 2 12s, 2 9s, and 2 1s. Everything shows up twice, everything shows up more than once, but none of them is the leader. They all are tied. If every single one of them is tied, there's no mode, because the mode has to be something that kind of is more prevalent than at least something else in the data set. So this is kind of an interesting little problem here, in my humble opinion. And of course, my humble opinion is the correct opinion. The last measure of the mid-range of central tendency is called the mid-range, and this one is just not interesting at all. You take the lowest, the smallest value in the data set and the largest value in the data set, you add them up and divide by 2. In other words, you take the average of the smallest and largest data sets, data values. Again, that's just not super interesting. Why would you want to do that? That kind of beats me. There doesn't seem to be a good reason for that. So if you looked at some of these scores here, I don't know why there's a dollar sign. This is the 5 factors that affect women's lives. So as you can imagine, women in the US, I would say generally, you know, it's not as bad to be a woman in the US as it is in some other countries. There are a lot of countries, even to this day, where being a woman there comes with a greatly reduced amount of rights. So there's factors that are brought together to decide, you know, if you were a woman, where would you want to live? The 5 factors are justice, health, access to healthcare, education, economics, politics. Using these 5 factors, all 165 countries were rated on a scale from 0 to 100. As you can see, Iceland is considered the best place to be a woman in terms of those 5 factors. The United States is not maybe as high as some of these others. Canada is considered a really good place to be a woman. The United States is still pretty high. I mean, it's maybe not perfect here, but you would certainly argue it's better than some other countries. You go to some countries over here, some of the worst places to be a woman. Chad has a score of 0. Afghanistan only has a score of 2. Yemen, the Democratic Republic of the Congo, Mali, the Solomon Islands, those countries are generally not seen as good places to be a woman in terms of, you know, those 5 factors: health, justice, education, access, etc. Now, if we just look in among the top places here, basically the places between France and Iceland, the mid-range is real easy. Just take the smallest value, 87.2, don't know why there's a dollar sign there, it's not a dollar amount, plus the largest value, Iceland is 100, add those things up, divide by 2, you get 93.6. Now, to be completely fair, I would imagine that a lot of these countries that are on the high list, like Iceland, Canada, Sweden, Denmark, I would imagine they're also good places for a man to live, because you're still going to have a lot of those factors. Like if the economy is good, it's usually going to be good for both men and women. So that's just an interesting idea. And there you have it. So let's queue up our next set of notes. We are moving on to the next section, 12.3. These are going to be measures of dispersion. So in the last case, we studied measures of central tendency. Where do the data values kind of cluster around? Where are they centered around? We argued why the mean and the median are the best two and when to use which one. The mode is a little bit tougher. It's interesting to introduce it, but the mode may not always be the best measure of central tendency for a small discrete data set. However, measures of dispersion, the word dispersion makes you think of how far out things are spread around. So measures of dispersion, these are also going to be measures of spread. How far out is the data spread? Are they all clumped pretty tightly together? Or are they kind of spread out way over a large range of values? So that's really what we're going to be studying here in this section. Measures of dispersion. Okay. So let's look at the range. The range is the most basic measure, and I think everybody in here has heard of the range before. It tells you how far apart are your smallest and largest values in a data set. How far do they range from each other, basically? And so the range is just rock simple. The range, you couldn't get easier than calculating the range here. You take your highest data value and you subtract your lowest data value. That's all there is to it. Some of these formulas aren't technically provided to you on the final exam because frankly, they are just so gosh darn rock simple that it's, I mean, to even know how to use the formula, you've already gonna have it memorized. So yeah, the range here is a very straightforward calculation. Largest value minus smallest value. Enough said. So here, and this is actually now outdated. Well, I guess age at inauguration. No, I guess this is dated properly. The 4 oldest presidents at the start of their first term. How old were they when they first took office? Trump was 70. Trump is the oldest president whoever took at the beginning of their term. He's about to be, I guess he is already 74 now. So yeah, that was kind of an interesting thing. Guess what? Here in a month, that record's about to be broken because Joe Biden is 78 years old. So he's going to be 78 and break Trump's previous record by 8 years. So that's kind of interesting. You kind of expect that, though, as well as time marches on because we have better health care. So you wouldn't expect a president to even live to 70 back in the 1800s in a lot of cases. So it makes sense that a lot of these presidents are maybe a little bit closer here. So then Trump, then you have Ronald Reagan, then you have William Henry Harrison, who, if I remember correctly, died within 12 days of being inaugurated as president from illness. He died. So then you have James Buchanan, who I don't believe had anything major going on in his presidency. And he was 65 when he was inaugurated. The range then of these 4 values is just 70 minus 65, which is 5. So among the 4 oldest presidents, they range in 5 years at the time they were inaugurated in age. Now, the range is rock simple, hilariously, stupidly easy to calculate, right? Largest value minus smallest value. Even if the numbers are ugly, just pop them into your calculator. It takes 2 seconds to calculate the range. Ironically, the next major measure of dispersion, the standard deviation, is much, much, much more complex than that. Much further, more complex, just insanely more complicated thing to calculate. What we're going to do is we're going to work on a calculation together. I'm going to show you the formula. It's on the next page here. For calculating, and even though I can show you the formula, you're still going to want to know 5 or 6 steps that break that formula down, how to actually use it. But here's the good news. At this point in the semester, I am happy to let you use your calculators to calculate standard deviation of a data set. What do I mean by that? Stay tuned. I'll give you an idea of what that's going to look like. If you have at least a scientific calculator or better, which you should have, it was required for this course, then your calculator should allow you to do these calculations here, to do this entire calculation very quickly. Before we can jump in and talk about the standard deviation, we need to figure out what a deviation is in the first place. What is a deviation? A deviation is the distance between a single data value and the average data value from the set. That's all a deviation is. So if you look back at the last data set, the president's ages, they were 70, 69, 68, and 65, the 4 oldest presidents at the time of their initial inauguration, or when they first took office. We need to calculate each of the individual deviations. So first, we have to calculate the mean. So I add up the 4 ages, divide by 4, you end up with 68. So the average age among these 4 is 68. Then we're going to calculate a deviation for each one. So for the age of 70, the first data value here, the deviation, you take the data value and subtract its mean. The next value, 69, you take the data value and subtract its mean. So each one of these, you take the data value and subtract 68 in each case. Sometimes it's going to go negative. That's okay. In fact, some of them have to go negative unless every data value is exactly the same. So you take the data item minus the mean, and you make a record of these. So what the standard deviation is it's kind of like the average deviation from the mean. The average amount that each data value deviates from the mean, except it does something weird and it's actually the squared average. It's the average of the squared deviations from the mean. And then there's even yet some little extra thing that's kind of pulled on you. You divide not by n, the number of data values, but by n minus 1. So here's what it really is. The standard deviation, you see this capital sigma, this what looks like a big E down here. What you're doing is you're taking each data value, subtracting off its mean, which is what we did here. We took the data value, subtract off its mean. You square each of these deviations. 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 3 squared is positive 9. You square the deviations, you add up all these squared deviations, that's what this E means. You divide that by the number of data values minus 1. And then on top of that, as a cherry on top, you take a square root of that entire computation. So calculating a standard deviation is a bit complicated. Now, technically, this is the formula for it down here. What these 6 steps do for you is it breaks down the formula down there so you can calculate it piece by piece and then end up with the final answer. Why do we divide by n minus 1 instead of just n? That's a great question. It's because secretly, if you were to go on studying statistics, what you're computing is something called the sample standard deviation, which is said to be an unbiased estimator for the population standard deviation. Those are things we're not going to worry about, but there is a reason it's n minus 1 down there, not just n like you'd expect. There is a reason, but the reason is beyond the scope of the course, we would say. So how do we compute the standard deviation for a data set? You would take the mean of the data items, you add them all up, divide by how many you have. You take each data item and subtract its mean. That's called the deviation. And you record each of those deviations individually. Then you take each of those deviations and you square them. Then you add up, you sum or add up all the squared deviations. Then you divide up this sum of squared deviations by whatever the sample size is, the number of data points is, minus 1. And then as a cherry on top, you take the square root of all that. It's an impressive process. It's an impressive process. If you look here, if you take your 4 data items, the 70, which was how old Trump was, 69, which is how old Ronald Reagan was at inauguration, 68, which was William Henry Harrison, 65, which was James Buchanan. We already calculated that their average value was 68. The average of those 4 values was 68. Then we need to figure out what each deviation is. It's the distance or the difference between the data value and its own mean. So you got 2, 1, 0, -3. We square each of these data values. When you square a negative number, remember when you square something, you multiply it to itself. You end up multiplying 2 negatives so it becomes positive. Your squared deviations will always be positive or perhaps 0, but never negative. You then add up all these squared deviations, which was 14. You divide by the number of data items minus 1. There are 4 data items, so we actually divide it by 3. We end up with 4.67. Then we take the square root of that business. And if we round to a couple decimal points, we end up with a standard deviation of 2.16. Now here's the lowdown. If you have a large data set, if you had 96 data values, here we only had 4 data values, so it's pretty easy. If you had 96 data values, 96 different numbers, do you think taking the standard deviation of that is going to happen quickly if you have to do it all by hand? Goodness no. You got to add up 96 values, divide by 96 to get the mean. For each one of those values, you got to find the deviation from the mean. So that means you have to do 96 calculations there. Then you got to square each of those, another 96 calculations. Then you got to add those all up, divide by 95, and 96 minus 1, then take the square root of that. If you have more than like 7 or 8 data values, good night. That could take you 10 minutes. If you had 96 data values and you were trying to do it honest by hand and you had plenty of scratch work, that could take you 30 minutes, maybe more. That's infeasible. That's ridiculous. So now that you've seen the process worked out, here's what I'm going to say. Here's what I'm going to say. I encourage you, Google calculating standard deviation, and then put your calculator model. So for instance, if you have a TI-84, the standard graphing calculator, or if you maybe have the TI-30X2S scientific calculator, you can Google, hey, how do I find the standard deviation? You could guaranteed you're going to be able to find a YouTube video. You can almost certainly find a YouTube video or a website with written instructions. There is a way to put the data values themselves into your calculator, then just have your calculator calculate the standard deviation. That's huge. All you got to do is feed the calculator the data values. So even if you have 96 data values, you do have to put 96 things into the calculator, which is a little bit of a pain. It's way better than doing it all by hand, exactly. Way better. You can feed the calculator the data values, and then you're basically putting them into a list, and then your calculator will calculate them. I would strongly encourage you to find that out for yourself. Now, I can show you how to do it if I knew what your calculator was, but everyone's doing different things with different calculators. A lot of modern calculators are equipped to make the process as easy and smooth as possible. So you are allowed to do that process for finding the standard deviation on the final exam. Now, remember, I am collecting your scratch work. So On the Scratch work, when you need to demonstrate how you got the right answer, you just need to say something like, oh, I use this function in my calculator. Don't just say calculator. Say, oh, I used stats, one var statistics in my TI-84 calculator. Okay, I know what you did then. Or, oh, this on this calculator, the scientific one, I put the data values in and then I had it calculate the standard deviation for me. Just be careful and know that what we want, the standard deviation is called S. It may also give you sigma, which looks like this, a lowercase sigma, the Greek letter. Make sure that you look at the S calculation. S is for the sample standard deviation. Sigma is for something called the population standard deviation. So just make sure you keep that in mind. Let's take attendance real quick. At any rate, so the normal distribution is a probability distribution. What is that? A probability distribution is something that lets you know how something ought to behave in terms of probability. How likely is this or that? How likely is it that this will take on a value greater than 4, less than -1? Something like that. That's a very general idea of what a probability distribution is. So what we look at with a probability distribution, we primarily start out by looking at histograms. Remember we said last time a histogram was basically a bar chart where the bars are touching, and we need them touching so that we can see the general shape that's going. So here's a random sample of 100 men, and this is a kind of distribution of their heights. The majority of men kind of fall under this here in the middle. They kind of clutter around in the middle here. It looks like this is called a little bit of a right skewed distribution. But as we increase the sample size, if I look at maybe 500 men instead, we're going to see if the heights of men are normally distributed, which they usually could be seen that way. If I keep increasing the sample size, I'm going to get more and more of this, what we call the bell curve shape. And in fact, the bell curve shape itself, the probability distribution for the normal distribution, is a perfect bell curve. It has this shape. It's nice and smooth about it. What it tells me is that the majority of values kind of flitter around in the middle here, and the taller you go, or the shorter you go on the x-axis, you're becoming less likely, because the height of the curve at that point is shrinking. It's getting smaller. So the normal distribution, the bell curve, which is the picture of the probability function for the normal distribution, is bell-shaped. It takes that shape. It's symmetric about a vertical line through the center. If something is normally distributed, its mean, median, and mode are all equal and are located at the center there, at the peak. There's two what we call parameters that create the normal distribution: the mean, which is the very center value, and the standard deviation. The standard deviation is your measure of spread. So as you increase the standard deviation, you're increasing the spread of the data. So if we look closely here, this green curve, this green bell curve, is very tall and it's very kind of bunched together and everything's closer together. It's not very far spread out. This green one would have the smallest standard deviation because there's the least amount of spread in the data. The purple curve has the largest standard deviation. The purple curve is content to be spread out nice and far like that. That would have the largest standard deviation. And the middle curve, the blue one here, would have a standard deviation in between. So, you know, Papa Bear's porridge was too hot, Mama Bear's was too cold. baby bear's porridge was just right. But yeah, the larger the standard deviation, the more spread out the data is, and the more it kind of looks like it's flat, but it's not fully flat. It still has a little bit of that bell curve shape. Now, what we have here, the 68, 95, 99.7 rule, AKA the empirical rule. The empirical rule is really interesting. You're going to have a mean and a standard deviation for data. They're both going to be numerical values. If I start with my mean here, if my mean is 0, and I go one standard deviation to the left of it, as well as one standard deviation to the right of it, approximately, or yeah, right about 68% of the data is going to fall within that range of values, between one standard deviation below the mean up to one standard deviation above the mean. If I go 2 standard deviations in either direction, here to here, approximately 95% of the data is going to fall within 2 standard deviations of the mean. And if I go 3 standard deviations away from the mean in each direction, which encompasses the previous levels, about 99.7% or almost all of the data falls within 3 standard deviations of the mean. It won't be 100% because theoretically, the normal curve, the x-axis is an asymptote for it, meaning if I kept going, the curve would never touch the x-axis. The area under this curve is going to be the percent of data that falls in a certain range. So we're looking for area underneath the normal curve. But we don't go into that uber level of detail. It's very useful, though, to know the empirical rule. So let's say that male adult heights in North America are roughly normally distributed, maybe not perfectly, but close enough for our work. So male adult heights in North America are approximately normally distributed with a mean of 70 inches. So on average, the average American male is 70 inches tall with a standard deviation of 4 inches. I believe it's much smaller than 4 inches. I think this data is wrong. But assuming this data is true, find the height that is 2 standard deviations above the mean. So if the mean is 70 and you want to be 2 standard deviations above the mean, that means you're going to be larger than the mean. You take double the standard deviation because we want 2 of them, and you add that onto the mean. So 70 plus 2 times 4, in other words, 70 plus 8, or 78. So a man, according to these numbers here, excuse me, a man who is 78 inches tall, which is 6'6", right? 6'6", which is very tall. A man who is 6'6" is 2 standard deviations above the mean. I believe the standard deviation is actually smaller than that, but using this data. Now, what's interesting is on this bell curve, we put 0, we put -1 to +1, -2 to +2. But what you can do is you can substitute in the actual numbers you have. So let's say that the distribution of male adult heights really is, on average, 70 inches with a standard deviation of 4 inches and is normally distributed. That means 70 is the mean, and that's what goes here in the very middle. If the standard deviation is 4, then one standard deviation below the mean is 66, 70 minus 4. One standard deviation above the mean is 74, 70 plus 4. That means that 68% of American men are between 66 and 74 inches tall, according to the empirical rule. So 68% of men fall in that range of heights, which is 5'6" to 6'2". It feels like it's actually a lot more than that, than 68%. If you go 2 standard deviations below the mean, you go 4 down, another 4 down, you're at 62 inches. 2 standard deviations above the mean, you go 4 up, another 4 up, you're at 78 inches. 95% of American men fall between 62 inches and 78 inches high, which again, that is a very wide range. 95% fall within 62 to 78 inches. And if you were to go 3 standard deviations below the mean at 58 inches, 3 standard deviations above the mean, 82 inches, 99.7%, or almost all adult men fall between 58 and 82 inches tall. That's how we can use that empirical rule. So yada, yada, yada. This is just expressing that idea. Now, when we take a specific data value and we calculate its z-score, we are actually calculating how many standard deviations it is away from the mean. And if the z-score is positive for a data value, if its z-score is positive, then it is that many standard deviations above the mean. If a z-score is negative, that data value is that many standard deviations below or less than the mean. So to actually compute a z-score for a given data value, you take the data value, subtract the mean off from it, and then divide whatever you get there by the standard deviation. If their data value happened to be equal to the mean itself, this top number would be 0. The standard deviation would not be 0. 0 divided by a positive number is 0. So the z-score for the mean is 0, because the mean is 0 standard deviations away from the mean. So the mean weight of newborn infants is 7 pounds. So on average, a newborn infant is 7 pounds. The standard deviation is 0.8 pounds. If the weights of newborn infants are normally distributed, we can compute the z-score for a baby who is born at 9 pounds. Now, real quick, we can look at the new bell curve we've made here. The average is 7 pounds. The standard deviation is 0.8 pounds. So 7 minus 0.8, 7 plus 0.8. 1 standard deviation of the mean, you're between 6.2 and 7.8 pounds. And thus, 68% of babies that are born are between 6.2 pounds and 7.8 pounds heavy at birth. You go 2 standard deviations below the mean, you're at 5.4. Above the mean, you're at 8.6. So 95% of babies fall between 5.4 and 8.6 pounds at birth. So anyways, the z-score for a baby that weighs 9 pounds, this is the data value, the 9. The mean is 7. We're going to subtract 7 off from 9 and divide by the standard deviation of 0.8. Since this baby weighs more than the average, we expect the baby's z-score to be positive. So we take the z-score, we take the data item, which is 9, subtract off the mean, which is 7, divide by the standard deviation. So 9 minus 7, you do that first, you get 2, divide by 0.8, the standard deviation. And so a baby who weighs 9 pounds has a z-score of 2.5. Put another way, that means that baby is 2.5 or 2.5 standard deviations above the mean. And so that gives you an idea of percentiles of how heavy the baby is. If 95% of data falls between 2 standard deviations of the mean, and this baby is 2.5 standard deviations above the mean, that's pretty rare. That's pretty rare. They're in a very top echelon of weight. The same could be said of IQ scores. If someone's really smart, you got a friend who's really smart, which means they like Pokemon. I don't know, maybe they do. Anyways, you have a friend and everyone's like, oh yeah, my friend's really smart. and they have an IQ that's 2.5 standard deviations above the mean, yeah, that is pretty smart because it's very rare to observe an IQ that high. That's 2.5 standard deviations above the mean. Don't tell your friend that, or they're going to get a big head. And, you know, it's kind of funny. A lot of really intelligent people are told their entire lives that they're intelligent. But no matter how smart you are, you don't just, unless you're born into a wealthy family, which nobody can control that. But no matter how smart you are, if you don't put forth any effort and you just kind of, you can get all A's and B's in school by not even trying. You don't have any ambition to get, to go get a further education or to get a good job or to work hard at your job. There's actually people who are born like freakishly smart tend to do no better than the rest of the population when it comes to success, economic success, specifically financial success. Because a lot of them are just, they get this big head that they can just do whatever they want. So they're like, oh, I could go get that really good job that's high paying and is what I want, but I know I could do it, so I'm just not going to do it. It's like, well, no, someone who may not be as smart as you on paper, but has a much better work ethic is going to take that job and be more successful in life. It's also kind of funny. There's actually an inverse relationship between intelligence and happiness, between what people rate as their happiness. There have been a number of studies that have shown that people who tend to score higher on IQ tests and are considered smarter tend to indicate that they are less happy. And there's a lot of reasons for that. Smart people, there's a lot of pressure put on smart people to succeed because, again, everybody around them is like, you're so smart. You should be a billionaire by the time you're 21. And it's like, I don't care how smart you are. It's not easy to be a billionaire by 21 if you're not born into money. Like, it's not going to happen for almost every case. Maybe there's a Mark Zuckerberg out there, but there's a lot of us who aren't going to be billionaires by 21. So a lot of smarter people will report that they feel a lot more stressed to succeed. So they tend to be less happy because of that. They feel that if they don't reach a certain level of success, that they're disappointed in themselves. So they report being not as happy. So it's kind of an interesting idea. Being born very gifted, who cares? Who cares how smart you are? Like, social skills are more important than natural intelligence. Anyone will tell you that who is highly successful. There's always going to be someone out there who's a freakishly smart genius that finds some magic stock market trick and becomes a millionaire, right? Yeah, and they could have horrible social skills. That's always going to happen, but it's not as common as you think. It's a lot more common that smart people who don't value social skills are going to be no more successful than the rest of the population. So anyways, that was just my rant. Oh, this next one's about IQs, intelligence quotient. Intelligence quotients on this special Stanford Binet intelligence test are normally distributed with a mean of 100 and a standard deviation of 16. So on this test, which is probably the gold standard for IQ tests, the average IQ score will be 100, the standard deviation will be 16. What is the IQ score corresponding to a Z-score of 1.5? Well, the negative sign in front of the negative 1.5 tells us that the IQ that we're trying to figure out is 1.5 or 1.5 standard deviations below the mean. So to figure out the IQ score, we're not calculating a Z-score, we're told a Z-score, and we have to go figure out the original data value. We take the mean, we go 1.5 standard deviations below the mean. So we go 100 minus 1.5 times 16, which ends up as 100 minus 24, which is 76. So if someone scores a 76 on this IQ test, they're 1.5 standard deviations below the mean. Let's also talk real quick about IQ. IQ doesn't really mean a whole lot. Your intelligence is not limited to how well you do on one IQ test. Those IQ tests are just, a lot of them are mostly logic-based questions. So maybe, you know, your aptitude for math, science, logical-based thinking can be somewhat predicted by an IQ test. But the IQ test takes no regard for like artistic skills, creative skills, things like that. And so you can score low on an IQ test and still be, you know, really successful in a field. Especially, I mean, imagine, if you're just a really kind of charismatic person who can talk to anyone, who can sell anything to anyone and get them to agree. You can go be a salesman or a saleswoman of expensive things, and you can make a lot of money even if you wouldn't score well on a traditional IQ test. Now, you still have to know what you're selling. You still have to be able to learn and study the product or the service that you're selling. But a lot of selling is, frankly, comes down to your social skills and your charisma, depending on what you're selling. So, yeah, don't think that IQ is everything in this world. It's not. That's silly. Intelligence is a much more layered idea. We can talk about something called percentiles. Percentiles for a given score is what percent fall below that. So if you scored a really good grade on a test, let's say you scored a 95 on an exam, and it turns out the 95 was in the 87th percentile. What that means is your 95 was better than 87% of students who took the exam. That's pretty good. Think about the SATs. If you remember the SAT, if you look just at the math English section, the SAT is out of 1600. If you score a 1470, that might put you in the 97th percentile, which means your score was better than 97% of people who took it. So depending on what it is, if you're talking about scores on an exam, you want to be in the higher percentiles. The 10th percentile then means you only scored better than 10% of people, and thus 90% of people scored better than you. So if you're talking about an exam, you don't want to be in the 10th percentile. You want to be closer to the 100th percentile. That's all a percentile is. A quartile specifically, you see the word quarter in there, dividing something into 4 pieces, 4 quarters in a dollar. The quartiles divide data sets into 4 equal parts. The 25th percentile is the first quartile, meaning the first quartile has 25% of the data below it. The 50th percentile is the second quartile, which, by the way, is also the median. The second quartile, the 50th percentile, are synonyms for the median. You can use a z-score for something in a table, and thus you can find percentiles for data sets. We are not going to go into doing this, though, because it's not going to be required of you. If you were to take a statistics course, then you could do percentiles. For instance, for the person who had a 76 IQ, you could find what their percentile is. Their z-score was negative 1.5. So you could look up their z-score, and you'll see that maybe 8% of people were scored lower than that. So that z-score of negative 1.5 is in the 8th percentile. And thus that IQ of 76 is also the 8th percentile. If you come up here and a baby weighed 9 pounds and their z-score was 2.5, you might find that they are in the 99.8 percentile or 99.9th percentile, meaning that baby weighs more than 99.9% of babies that are born. And so they're at a very high weight, which is not necessarily bad or good, it just depends. You'll find a couple of different things, but if you're talking about polling data, and you want to talk about something called margin of error, again, we're just touching on this a little bit. We are not going wild with it. There's this cute little formula. I would, question its validity. But in a random sample of 1,172 children ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. So kids age 6 through 14, they're asked, what's the what's one of the bad things about being a kid? And 17% said being bossed around. Well, I would say, well, you're a kid, so you're going to get bossed around because you don't know anything because you're too young to know. Oh, you don't like being bossed around when you try to touch that burner that's turned on? Oh, my feelings are so hurt. No, you're going to get bossed around. You're just going to live with it. So yeah, kids are like, I don't like being bossed around. And I say, wham, get over it. It's better than, no one ever giving you any guidance or helping you or any kind of way like that. Anyways, I'm rambling. The margin of error, so 17% say that they don't like getting bossed around. The margin of error has this slick little formula. You do 1 over the square root of the sample size, and then you multiply that by 100%. So in this case, the margin of error would be about 2.9%. And what that means is we take 17%, the average value, and we subtract 2.9%, we add 2.9% onto it. And thus, while we only sampled 1,172 kids, that's not the entire US population of children. So I can't say for certain that 17% of the US population of children don't like being bossed around. But I can say I'm 95% confident that somewhere between 14.1% and 19.9% of US children don't like being bossed around. So the margin of error gives us kind of a range of values that that poll data or things like that can fall into. Again, though, until you take a statistics course, you're not going to really truly understand margin of error. But then margin of error becomes a very important concept in a broader statistics course. So we're just trying to kind of give you a little bit of a taste. Now we looked over here. And we were looking at the nice bell curve. Boy, that bell curve is beautiful. You wake up 6 in the morning, you put on a pot of coffee, you make your delicious Folgers coffee, and you see the sun glistening off that bell curve out there in the distance, and a little tear falls down your eye because that bell curve is gorgeous. It's beautiful. It's symmetric. And when you know something follows the bell curve shape, you can predict a lot about how that something behaves. But the bell curve, while it does show up quite a bit, especially for sums of things, not everything is going to follow a nice bell curve shape when you look at its distribution. So what we see is that if you're looking at, say, the weekly earnings of people in the United States, there's going to be some people who make just a laughably massive amount of money. And while they're very rare, so the height of the curve isn't very high there, the fact that the curve is, the fact that those values exist at all, even though they're rare, really pulls on the distribution curve. Imagine you had the normal distribution, and then you just went over here and you pulled the tail to the right, but not on the left here, just on the right. That's going to give you, in this case, what is called a right skewed distribution, where it's being pulled to the right. The mean, median, and mode all suddenly go into chaos. They're no longer the same thing as they were before. So that's how we create skew in something. Again, not something we investigate in detail in this course. You'd have to take a statistics course to see how being skewed right and being skewed left, what that means for the data you're working with. The last thing we're going to do today, so we're actually done with lecture. That was it for chapter 12, and that's it for lecture, but we're not done.